Consider then a simple rectangular barrier. We have a potential height V0 here. We have possibly incident and reflected electrons on the left and transmitted electrons on the right, and perhaps the barrier is a thickness Lz. We presume we've got some incident electrons with energy E. And we presume, at least for our present discussion, that these are below the height of the top of the barrier. So E is less than V0. And on the left, we expect to have this kind of form for the solution of Schrödinger's equation, with a forward propagating wave and a backward propagating wave with wave vectors k. We also have presumed here no electrons incident from the right, so we have only transmitted electrons over here, and the solutions in general for forward-going electrons on the right would have wave functions in this form, just a forward propagating wave. Possibly this k here might be a different k, here kr, from the one on the left, although if these potentials are the same, it won't be. It'll be the same k. We could have a more complicated barrier, perhaps something that looks like this. We might keep the same top height here for our discussion, V0. And still we would presume that E, the energy of the incident electrons, is below V0. But we might have this much more complicated potential on the right, and we might end up with a different wave vector kr down here. Suppose then that we have solved this problem and found the relations between the amplitudes of the incident and the reflected waves on the left and the transmitted wave on the right. In this square barrier, we know how to solve that, and we would end up with decaying exponentials, which would be these ones, and also decaying from the other direction, or growing in the mathematical sense, exponentials, with the d here. And we presume we might have done this in even this more complicated case. Somehow we deduced the relation between these constants here. How do we relate these constants, a, b, and f, that presumably we have solved for, or at least their relative values, to actual electron currents? Well, previously we derived that the particle current density in quantum mechanics for a wave function psi is given by this expression. And psi here can be a wave function in both time and space. So it can be a full time-dependent wave function. Incidentally, this is particle current density, not electrical current density. If we were talking about electrons, if we multiplied by the electronic charge, we could turn this into an electrical current density, but here it's a particle current density. So if we consider particles of well-defined energy E, which actually means they must be in energy eigenstates with eigenenergy E, then the wave function will take the well-known form with a purely spatial part multiplied by a time-varying complex exponential e to the minus I e, the energy, d over h bar. So in these products, psi grad psi star and psi star grad psi, the term e to the minus I e t over h bar from the psi will be multiplied by its complex conjugate from psi star, and those will multiply to give 1. So then this expression simplifies just to the same expression, but only with the spatial parts of the wave functions in here. If we consider only a one-dimensional problem, for example for a potential varying only in the z direction, we need only calculate the current in the z direction. And we could call that particle current just the scalar Jp, which we will understand now to be current density, particle current density, in the z direction. So we simplify our vector expression to a simple scalar one, and incidentally these gradients in here will now just be d by dz. For a simple barrier like this one, with the same potential on the left and the right, which we will take to be 0 just for algebraic simplicity, it doesn't matter what we choose it to be really, And for a particle of mass m and energy E, we have, as usual, that the energy will then be h bar squared k squared over 2m. With the wave on the right in this form, f e to the I kz, because we've decided indeed these are the same potentials, then from this expression here, and noting that psi grad psi star will just be this expression here, well, we can perform this differentiation here that gives us an e to the minus ikz differentiated as minus ik times the e to the minus ikz. The complex exponentials we're left with multiply up to 1, and so we have this simple expression here for the evaluation of this term here. And similarly, we can evaluate the other term. We will get a plus ik in that case, but since these terms are one minus the other, these two actually will add up to give us a total of twice this one value. We will get jp mod f squared h bar k over m. We've cancelled out the 2 because these two terms actually ended up adding one another. On the left, with psi of z as a e to the ikz plus b e to the minus ikz, from this same expression here, we have a slightly more complicated looking expression, but in fact it simplifies out when we multiply everything together. We are in fact only left with these two terms. The cross terms, for example, b e to the minus ikz times minus ik a star e to the minus ikz, are cancelled out by opposite terms, like this one here. This product will give a cancelling term. And so all that's left is this pair of modulus squareds, one minus the other, for our current density. Note that all the spatially oscillating terms have actually cancelled out. The net current is not varying spatially on the left. That might surprise you if you remember the kinds of solutions one gets in these kinds of problems, which often have a standing wave of some kind on the left that looks as though the probability density varies in space. And indeed, the probability density does vary in space. But somewhat surprisingly, the current density actually doesn't. Since we've deduced this current density here, we can therefore consider h bar k mod a squared over m as the forward current on the left, and h bar k mod b squared over m as the reflected or backward current on the left. That gives us a consistent interpretation of what's going on. And adding the two together gets our net forward current here. If we think about how this relates to our ideas of group velocity, and we use this expression for the energy and equate it to an h bar omega, for omega being the effective frequency we're working with here, then we can deduce a group velocity. We know that group velocity is d omega by dk, and in this case here, from this expression up here, we would simply conclude that the group velocity is h bar k over m. So the currents could, if we wanted to, be written as a forward current that is actually mod a squared times the group velocity, a backward current whose magnitude is mod b squared times the group velocity, and a transmitted current whose magnitude is mod f squared times the group velocity. But in fact, remember, we have not actually used group velocity to deduce anything about these currents. That's an interpretation after the fact, one that makes some sense, but we did not use group velocity to derive these current densities here. We did it directly from the wave functions. With these forward and backward currents here, the fraction transmitted by the barrier can be written as an eta here we're going to use is the current not reflected divided by the instant forward current. So if we know the instant forward current and we look at the current that is not reflected, then we have an expression like this, which corresponds therefore to the transmission through the structure. So this was the net forward current when we subtracted the backward current from the forward current, and this was the incident forward current. This current that is not reflected must be transmitted. It might seem more obvious to write with this forward current and this transmitted current here that the fraction transmitted is the current transmitted over the instant forward current. And indeed that's true in this case, and we could write it like this. For a barrier with the same potential and material on both sides, these two expressions actually will give us the same answers. You could prove, in fact, that they're equal for a problem like this, for example. Or even if we don't know precisely the form of the barrier in here, if the potential is uniform and the same on both sides, both of these formulae will, in fact, give you the same answers. But if we take a problem like this, where we have a different potential or material on the right, the group velocity might be different on the right, or it might not even be defined in some complicated cases, and we can show one of those later. While we might handle that situation, there are ways we could deduce all of this from the forward current. This expression is always correct and avoids these issues. As long as our potential is uniform over here, it doesn't actually matter what happens to the potential over there. If we knew A's and B's that were solutions of this problem, we could deduce the transmitted current from this expression. And it is often otherwise just as easy to calculate this as it is to calculate that one in practice. For example, we could have the situation we get in field emission tunneling. Field emission is when we emit through a barrier that is tilted by the application of an electric field. This could happen at the surface of a metal, for example, with a field in the vacuum that is trying to pull electrons out. The potential diagram would look like this. In this case, the barrier might continue its slope for a long distance, giving no actual constant group velocity in the right anywhere. Here, however, this expression will always work. It might seem here, at least for the simple barrier, that we are merely proving the obvious. We have currents that make sense with group velocities, and we might think we could have figured these out more simply, perhaps almost using some classical approach. Note, however, that even though we've connected to some classical ideas, we've not used those classical ideas to deduce the results here. We have instead rigorously deduced the current densities by a first principles quantum mechanics method, without actually relying on any separate notions of velocity. Armed with these results, now we can consider tunneling with much more complicated barriers.